In the previous two videos, we looked at the midpoint rule and also the trapezoidal rule to be able to approximate definite integrals. The last numerical method we're going to look at is Simpson's rule. Rather than using a trapezoid or a rectangle, Simpson's rule is going to use parabolas. All right, and what that's going to do is it's going to kind of conform to the curve at that given point. All right, and of course, the more parabolas we have, the better the approximation is going to be. All right, so now what it does, and I'm not going to go through the algebra for this, but we pick 3 points that are going to fall on the curve, and we create a parabola, okay, to represent the area bound by that curve. And you can kind of see that in this diagram below. And then what we try to do is we try to do a polynomial interpolation to be able to find that area. All right, so now rather than go through the rigorous algebra that's necessary to do this, let's just go through and assume that the formula is correct. And we will see after we do a few examples that it certainly works. All right, so 2 main differences between Simpson's and trapezoidal rule. Number 1, we're dividing by 3 instead of 2, so it's got delta x over 3. And then the coefficients are going to alternate inside. So the first one and last one are still 1, but then we have a 4, 2, 4, 2, 4 pattern. All right, so we're basically going to alternate 4s and 2s until we get to the end of this. Okay, and that's just a result of the algebra from the formula for this. Okay, so let's take a look at a couple examples that use Simpson's rule to be able to approximate definite integrals. And once again, what we'll do is we'll try to figure out what the area is. Okay, so I'm sorry, the error. Excuse me. We're going to find the area as well. So we have a function f of x equals square root of 1 plus x cubed over 2 to 6 and the x-axis. Okay, so analytically, it might be difficult for us to figure this out. So numerically, it might be easier. We're going to do all the same stuff that we did in the previous 2 videos. So we're going to find definite integral, area, approximation, and then we're going to approximate, in this case, S4 and S8, and then we're going to find the percent error. Okay, so just like we did in the previous videos, let's use Wolfram alpha to be able to approximate this. Okay, so we're going to have a square root of 1 plus x, and I missed a parenthesis here. So square root of 1 plus x cubed. And we're going from 2 to 6. Okay, so those are our bounds. All right, and it gives us that it's a Fibonacci sequence, which is, or some sort of, with these parameters in here. All right, but moreover, we're really just interested in this. All right, so the values are pretty big. All right, and you know the function really still behaves like x to the 3/2. So it kind of rapidly does increase. Plus, we're going from 2 to 6, not from 0 to 1. So we might have a little bit more error than we did in the previous examples, but we might not. Okay, so anyway, getting back to it for part A. All right, so we have our function that looks something like this. All right, it's kind of linear. Okay, so let's say this is 2 and this is 6. All right, and then it's going to do like this behavior. But the area that we're interested in is right here. All right, the integral, pretty easy. From 2 to 6, square root 1 plus x cubed dx. All right, and then finally the approximation, which is at 33. Oh, I think I accidentally hit print instead of erase. So let me get rid of this, just so that way you can read it, or at least pretend to. All right, and so this is going to be 33 point. I think it was 3058. All right. What's going on here? There we go. All right. Okay. So that's going to be our approximation. All right. So next thing we're going to do is we're going to, and this is part B as well. Okay. So this is just like a hybrid of A and B. So now we're going to use Simpson's rule. All right. And before we could do that, we have to find delta x, and then we have to find the unit marks. Okay. Just like we've done the previous. Delta x is pretty easy. Okay. So this is part C. And so delta x is going to be equal to 6 minus 2 divided by 4, which is n, which is 1. All right. So that makes things really easy for us. So to be able to figure out Simpson's rule, so I'm going to call this S4. That's going to be equal to delta x over 3. All right, so remember, we're not dividing by 2, we're divided by 3. And we're going to have a function at 2 plus, now remember, we're going to alternate 4s and 2s. And we're just going to add 1 each time. Okay, so it's 4 functions at 3 plus 2 functions at 4 plus 4 functions at 5. And then finally, the function at 6. And see if we can squeeze that in there, just did. Okay. All right. We're going to use Excel to be able to approximate this. It might not give us a really good approximation because remember, this is rapidly increasing and the delta is pretty large. All right. So we have a delta of 1 here, but let's see what we get. Okay. So this is going to be 1/3 of, now we're going to go into Excel. Hopefully it's going to help us to do it. All right. So just type in our bounds, which are going to be 2, 3, 4, 5, and 6. And then this is going to be equal to the square root of 1 plus a1 cubed. All right. And these are going to be our values, which is good. They should be fairly large. All right. Now remember, we have to have the multiplier. So 1, 4, 2, 4, 1. All right. And again, those are the coefficients for each of these animals right here. So 1, 4, 2, 4, and then 1 here. So it's going to get even larger. Remember, we're just going to use B1 times C1 to multiply those and make sure you have your equal sign in there. And then finally, just drag this down and we're going to get a sum of these values. All right, so we get 99.9. Now remember, we have to divide that or multiply it by 3. So that's actually pretty good. All right, so we get 99.92133. And then I'm going to say 4, and I'll cut it off there. All right. And this is actually going to turn into something pretty close to the 33.3, right? Okay, even though the tick marks are pretty large. So I'm going to say 1/3 or equal 1/3, 1/3 times this cell right here, okay, which is D7, 33.3071115. Okay, so this is going to be 33.3071112 if I was to approximate the 6 decimal places. All right, and so notice that we're really close actually. Okay, by using Simpson's rule, we're actually accurate out to the hundredths place, and even the thousandths place is only 2 thousandths off. So that's pretty good. Let's do the same thing. Okay, so for D, we're going to find S8. All right, so we're going to change our delta x. So delta x is going to be 6 minus 2/8. That's going to be a half, right? And so our function, or I'm sorry, our S8 approximation is going to be equal to delta x over 3, so a half of 3. And then we're going to have the function at 2. And then we're just going to keep adding a half each time. So 4 functions at 2.5 plus 2 functions at 3 plus 4 functions at 3.5. And you're just going to keep doing this pattern, okay, until you get to 4 functions of 5.5, since we're going up to 6. Right, so this is going to be 5.5. And then we have our function at 6. All right, so now of course Excel is going to do the lion's share of the work here. Okay, so this is going to be a 6. And we're going to go back to Excel. We're going to change all of our unit marks. Okay, so this is going to be 2, and then 2.5, and 3, and 3.5, and 4, and 4.5, and 5, and 5.5, and 6. All right. The good news is Excel was smart enough to be able to compute the function. We're just going to do our 4, 2, 4, 2, 4, 2, 4, 1. Okay. And then what we're going to do is we're just going to drag this down. Okay, so we're just, because remember, we still have the product here. Okay, so we're just going to drag that. It's going to fill in over the sums that we had from before. And then finally, we're going to add these up. Right? So we take the sum of all of these. Okay. Now this is just the interior part. We still have to take a sixth of this. Okay, but it's looking pretty promising. Okay, so the value we end up with is going to be our 199.835278. Right, and then moment of truth. Let's take a sixth of that. So this is going to be equal to 1/6 times this number right here, which is in D11, and we get 33.035879. All right, so let's, I don't remember the exact value, but I do remember it was 33.305. All right, and then we have 8796, so that's going to be 880. All right. Now, going back up, 3058, 3058. All right. So this is actually an even better approximation. All right. So check this out, how good this is. This is actually exact up to whatever we're given. All right. Wolfram Alpha just didn't give us any more. All right. If I really wanted to, I could try to pick another piece of technology. All right. So and I'm wondering if I can expand this value just by clicking on it. Oh, here we go. We get a little bit more out of it. So what I did was I just went over here and I just clicked on this value. It just underlines it for you and gives you a little bit better approximation. So let me go back up here and I'm just going to approximate this to 6 decimal places. So we have 30578 1. So let me make sure I copied that. So 305781. Yep. Okay. So that's pretty close, I think. All right. So if I was to compare this, okay, so we got this is T or S8, excuse me. Right, so this is going to be our S8, and then we got 33.3057. All right, so it looks like it's accurate to the thousands place. Okay, but with rounding, 305,780. All right, if I was to round it, okay, just to that 10,000s place, it would still be accurate. All right, so now the last thing we got to do is we got to get the percent error. Okay, so let's get the percent errors for this so we can be done. Okay, so this is for S4, right? So we're going to take our approximation, which is the 33.307112. We're going to subtract out the 33.305780, and then we're going to divide it by 33.305780, multiply it by 100%, and that's going to give us our percent error. Okay, of course, the error is more important than anything, just because if it's not a good approximation, we certainly don't want to use it. All right, so just going into our Excel, right, I'm going to say equals. So we have our 33.307112, and I'm typing it on the other screen, 33.305780, and we're going to divide it by 33.305780. All right, and this is what it gives me. It gives me 3.999, and I have to multiply that by 100. Okay, forgot to do that. All right, so 0.00399, so 0.004%. All right, so the error here is 0.004%. All right, and that's just for S4. Now for S8, we're just going to change the first number to this animal right here. All right, so that's going to be for S8 error, it's going to be 33.305880 minus 33.305780 divided by 33.305. 780. And I'm just going to use Excel one last time. And I'm just going to change the first number. So 33,305, 78. I'm sorry, it was the first number was 880. Sorry, they're really close to one another. Okay. And this time we get 0.0003%. All right, so this is going to be approximately 0.0003%. All right, so essentially, as long as we're not doing anything that risks people's lives, these are both extremely good estimates. All right, from my experience, Simpson's rule usually does the best job in approximating these definite intervals. And so the question is, well, why do we even have the other two? Well, it's just a way for us to check to be able to make sure that our estimates make sense. But also there may be functions to where a trapezoid or a rectangle might be more appropriate than some sort of parabola. Okay, so keep that in mind when you're doing this, is that Simpson's rule usually gives you the best, but the other two might have uses as well. All right, so that's everything for our numerical method stuff. Hopefully this helps you to be able to do your assignment work and also to be able to prepare for your quizzes and exams.